Okay, now we will move to the question. Okay. So this is our question. So here CT is given as 50 cos 25. This is F. Okay, it is 10,000. And MT is given as 10 cos 25 500 T. Okay, so this is 1 kilohertz, 10 kilohertz signal, and this is 0.5 kilohertz signal. Okay, so you can see that the frequency. Okay, so this is the FC frequency and this is the FM. Okay, so you can see that FC is very much greater than the FM. Okay, so carrier frequency is very much greater than the information signal, message signal frequency. Okay, and this also a condition. Okay, in a modulation, this also a condition. Okay, and also we know other condition that mu, that is AM by AC, should be less than 1. This is another condition. Okay, so these two conditions should satisfy in a modulation to detect the envelope correctly. Otherwise, the distortion can happen and we can't correctly detect the envelope. Okay, so in theoretical analysis, I forgot to mention this. Okay, so we now to know it. Okay, so we will know. Okay, so here we are asked to write the complete modulated waveform. Okay, so here we have, so we know the modulated waveform. Okay, that is XAMT. We can write it as AC cos omega CT plus AC mu MT cos omega CT, like this. Okay, so we can write it in this manner. Okay, so here the MT also a sinusoidal signal. Okay, so this MT also a sinusoidal signal. I will get the general form. So it is like AM cos, here omega C now in 25 FC manner. Okay, so I will get the same cos 25 FCT, and here also we get 25 FCT. Okay, so this I get. Okay, so here we have AM cos 25 FMT. Okay, so this is the amplitude of the modulating signal, and this is the frequency of the modulating signal, and this is the amplitude of the carrier signal, and this is the frequency of the carrier signal. Okay, so so if I substitute this sinusoidal at for this MT, okay, I will get that total AM signal as, so here I have cos 25 FCT plus AC is there, mu is there. Okay, AC mu is there. Okay, and here the MT is AM cos 25 FMT. Okay, and also we have cos 25 FCT. Okay, so we will get this. Okay, so but some mistake is there. That is this AM. Okay, so you know that this mu, okay, this mu is defined as AM plus AC. Okay, so if I apply the AM also here, so I have AC there, AC this part, AC, AM by AC, that is mu, and AM is there, this AC cancelled out, and I get AM square. Okay, AM square instead of here. So I get AC, okay, AC AM square. Okay, AM square. So if I get the modulated signal, I will get this maximum signal. I will get AC plus AM square. Okay, for example, if AC is so here AC is 50 volt and AM is 10 volt. Okay, so if I get the maximum, so if I get this one AC plus AM square, I will get 50 plus 100. Okay, I will get 150. Okay, in next session in MATLAB you can view this. Okay, in MATLAB program you can view this. Okay, uh, so this is wrong. So if we get the A min, okay, it is, we come here, it will be minus mu, no, minus mu, and it will be AM square minus, so it will come AC minus AM square. Okay, so I will get 50 minus 100, so I will get minus 50. So if we draw the envelope, okay, in this case, okay, it will start like here and go and cross this T line, again come. Okay, here it's go and cross this and come. So you will get this distorted signal. And in MATLAB program also you can see at this point there is a phase shift like this in carrier signal. Okay, so this is wrong. Okay, it is over modulation. Okay, this is called over modulation. I actually at that part also I forgot to mention it, the analysis part. If this come, it is called over modulation. If this mu is more than 1, and it is it is greater than the 100% modulation. No, if this mu is equal to, it is the 100% modulation. So if this mu is greater than 1, it is, we call it is more than 100% modulation. So we called it over modulation. Okay, so this is the over modulation scenario. Okay, so what is the wrong actually? Put in this AM here. That is the only wrong. Okay, so at the beginning, I told you that, okay, in the tutorial session, in live tutorial session, I mistake this. Okay, that is why I re-record this session. Okay, I want to emphasize this to you. Okay, because I put the same here at the live in our live tutorial. Okay, so I want to recorrect that mistake. That is why I re-record that tutorial. Okay, so put in AM is wrong here, so we have to remove this AM. Okay, so we will get only this terms. Okay, so you can see that in our live tutorial also we see that using cos alpha plus beta and cos alpha minus beta, these are two well-known trigonometric identity, cos alpha cos beta minus cos alpha, sorry, minus sin alpha sin beta. Here you have cos alpha cos beta plus sin alpha sin beta. Okay, so using this we can write this, okay, as a cos alpha plus beta terms. Okay, so we will get like this total A modulation, okay, as AC cos 5 FCT plus. Okay, so here it come half. Okay, because if you add this, okay, if you add this one and this one cancelled out, and you will get 2 cos alpha cos beta, but here it is 1 cos alpha cos beta terms. So you have to divide this cos alpha plus beta plus cos alpha minus cos alpha minus beta terms by 2. So you have half this AC mu is there. So I will get that AC mu. Okay. So here we have cos alpha plus beta, that is 25 FMT, 25 FCT. So I can get 25T here, and I have Fm plus Fc. Okay. And also I have half AC mu. Okay. Here I have cos alpha minus cos beta. So alpha should be this one, 25 FCT. Okay. It is the greater one. FC is the great, if FC is greater than FM. Okay. So if I get 25T out as usual, because it is a common fact. Okay. So I will get 25T I get, and I have FC minus FM. FC minus FM. So you can see that, okay, for this signal, if the information signal, baseband signal is a sinusoidal signal, AM cos 25 FCT likewise signal, you will get two sideband. Okay, and this is one. This is the carrier part. This is the carrier waveform. In addition to this carrier waveform, you have two sideband. This is first sideband. Okay, let's say this is V1, and this is the second sideband, SP2. So this is the complete signal. Okay, and I think this one also correct. Okay, if you write it up to here, that's also correct. Okay, so in future we will use this. Okay. Okay, so we will go to the next question. So we have done this. Okay, so we will go to the next section. So find the power of the carrier signal. Okay, so you have to find the power. Okay, so again we have to go to our signal and system tutorial. Okay, we have to remember some stuff we learned at signal and system subject. Okay, that is power of a signal. Okay, so energy of a signal also there. Okay, so energy of the signal we can evaluate as minus infinity to plus infinity. If we have xt signal, time domain signal, so we can get xt absolute d square dt. Okay, so this is the power signal. Okay, power of this xt, energy of this xt signal, energy of xt signal. And if you want to find the power, okay, you will get that. So power is energy divided by time. Okay, so to evaluate power, you have to consider time duration of that xt. Okay, let's say we get t time duration. Okay, so we will get it like this. If this t limit to infinity, okay, and it should be divided by t and minus infinity to plus infinity, xt square dt. Okay, so this is the power signal. Okay, so just give me a moment. Let's see it is correct or not. I can't remember. So we have to go to the signal and system. So it is should be under the signal classification. Okay, here we have energy and power signal. Okay, so here we are only focus our study to the continuous signal. Okay, so you can see that this is the energy of xt signal, normalized energy. So it is okay. This is the normalized energy content of the xt signal. Okay, so it is okay. And this is normalized average power. That one also correct, no? 1 by t, 1 by t, xt is, yeah, that's correct. Okay. So my memory is okay. Okay, here it is absolute 1 by t, and we have to integrate this section with t. Okay, so so if this xt, okay, so this is the general expression for find the nominalized power content of this xt signal in certain duration, in this t duration. Okay, so if this xt is a periodic signal, and the period is t naught, okay, and the period is t naught, we can prove that power content of the signal is equal to, okay, 1 by t minus c square to plus, sorry, 1 by t, it is not minus infinity plus infinity, it is with t naught. Okay, here it is 1 by t naught period. Okay, t naught, and it is equal to xt square dt. Okay, so this is for periodic signal. Okay, so if this periodic signal is a real signal, okay, for real signal, this xt square, and for real signal is xt absolute square is equal to xt square. Okay, xt square. So for real signal, we can write this as p is equal to 1 by t naught within t naught, okay, x square t dt. Okay, so we are going to use this identity to calculate our power, because for both signal we have periodic signal, cos signal, sinusoidal signal. Those are periodic in nature. Okay, so and also we have real signal. Okay, normally oscillator can generate only real signal, it can't generate complex signal. Okay, so this is a real signal and periodic signal, so we are going to use this signal. Okay, so I think it is better to keep remember this identity. Okay, how to find a power content, nominalized power content of periodic real signal. We have to do this integration. Okay, so we will do it. Okay, so we will do it. Here we have 3 parts. Okay, here we have 3 parts. Okay, so first we will get this carrier part. Okay, so now we are going to find the carrier frequency. Okay, so we are going to find the carrier frequency first. Actually, we are asked to find that one, no? Find the power of the carrier signal. Okay, so we have to find the power of carrier signal. Okay, so this is the carrier signal. So I will get that separately. CT, this is the carrier signal. Okay, so I will get the general signal. It is CC, AC, cos 25 FCT. Okay, so this is the carrier signal. Okay, this is also a sinusoidal signal and periodic signal, and also a real signal. Okay, so I can get the power of this carrier signal, power of carrier signal as integrate. Okay, so I get, so this is 25 FC, no? It is a cosine signal, no, like this. So this signal is like this. Okay, so this is one term, and this is another term. Okay, so this is 25. Okay, so if I write the cos signal, it will look like this. Okay, if I write the cos signal, it will look like this. Okay, I will get this, 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 this. Okay, so cos signal I will get like this. Here it 0. Okay, then here. Okay, then here, and then here. Okay, and also then it here, and it goes here like this. Okay, so this is a cosine signal. So if we consider this, okay, this is the period, no? This is the period of the signal from here to here. Okay, from here to here. This is the period. So this is a one cycle, no? This is a one cycle. So this is the period T. So it is for 0 to 2, 5. If we consider cos t, okay, respect to t. Okay. So I get one period to find the nominalized power content of the signal. Okay, so we have 1 by t naught. Okay, 1 by t naught. Okay, so that is this time. Okay, that is the time, this time. Okay, so if it is theta, it is 0 to t5, 2, 5. But if this theta is equal to 2, 5 FCT, this is not equal to 0 or 2, 5. Okay, so it equal uh, at this time t is equal to 0. Okay, at this time t is equal to 0. So here t is equal to 0. Here t is also equal to 0, and at this time this theta is equal to 5 by 2. Okay, so this theta is equal to 5 by 2, and here we have 5 FCT, then 5 cancel out. Okay, then t is equal to t is equal to 1 by 4 FC. Okay, so this value we get 1 by 4 FC. Okay, and this will you will get FC 1 by FC, and this is 1 by 4 FC. This is 2 FC. Likewise, you will get. Okay, I think we have write this waveform uh, in our first tutorial. Okay, so I think now you can write, okay, this kind of wave. Okay, so here I just, for simplicity, I just take it as 0 to 2, 5. I take this t as a theta, but this theta is equal to 2, 5 FCT. Okay, so if you find the t, it is not 0 and 2, 5. Okay, so if it has a problem, please refer our first tutorial. Okay, so here we have drawn some time domain signal. Okay, so you can refer that. Okay, so okay, so here this is from 0 to t naught. Okay, I will get it as a t naught. So we have our signal CT, and we have to get the C square T. So I will write it directly. So I square this. So we have a C square cos square 2, 5 FCT dt. Okay, so we have to evaluate this. So you can see that this AC is a constant, but this is not a constant. So here you have square value. Okay, to integrate this easily, we can convert this to, we can remove this square. We have we have this trigonometric identity. Cos 2t is equal to cos square t minus sin square t. Okay, So cos sin square t is equal to minus, sorry, 1 minus cos square t. Okay, so here we can write this instead of this sin square t, 1 minus cos square t. Okay, so we have cos square t minus 1 minus minus plus cos square t. So you have 2 cos square theta minus 1, and it is equal to cos 2t. So cos square t you can get as half cos 2t minus half. Okay, so you can get this uh, value using this identity, using this trigonometric identity. Okay, so I use this here. Okay, so PC I have, okay, so PC I have 1 by t naught, okay, 0 to t naught. So here I have AC square, so I will get it out, AC square. Okay, I get it out. So I have half, okay, I have half. So cos t here it is plus, no, this one is go to this way, then it is plus. Okay, so when this one is going to one, when this one went to this side, okay, it will be plus cos 2t plus 1. Okay, so I have half cos 2t, okay, plus half dt. Okay, so instead of cos square 25 fc t, I can write this. So here theta is 25 fct, that means 25 fct. So here 2 is also there, so it will get 45 fct. Okay, so I will write it again. Okay, so PC is equal to AC square by T naught. Okay, 0 to T naught. Okay, so half is there, I get out the half also. So cos 45 FCT, cos 45 FCT. Okay, so here half plus value is there, so I will get the plus. So all these things are there. AC square to T naught, and half I will get out again to T naught. Then I will get 0 to T naught 1 dt. Okay, so this expression we get. Okay, so if we integrate this, what happened? Okay, so you can see now, previously it is cos 2t, okay, 25 fct. Now it is cos 45 fct. That means the frequency is doubled. No, for this signal, for this cos 5 fct means the frequency fc, it is now 2 fc. Here it is fc, frequency is fc, now here 2 fc. Okay, here the frequency is fc. Okay, here the frequency is fc, and here 2 fc, 2 fct. Okay, that means frequency is double. So if this is cos 25 fct signal, if this is cos 25 fct signal, okay, if we draw the cos 45 fct signal, what is there? Okay, that means within this circle, 2 circles should be there. No, here it have 1 circle. The frequency double means in this area 2 circles should be there. Okay, so here you have like this one also you have to keep like this. No? So you have this one, and then and here you have like this, no, like this. Okay, then you have this. Okay, and it come to here. Okay, and you have this, and it go to here. and you have this over here, and again you have this. I think it's a mistake. Okay, so I will draw it again. I will remove all these things. Okay, so here we have, okay, so I will get this one, this one, okay. So our first signal is like this. Okay, it is like this one, this one, and this one, and it is in this way. Okay, okay, it is like this. Okay, so this is cos 25 FCT. This is cos 25 FCT. So now we want to draw. Now we want to draw cos 24. Okay, 25 to FCT. That means here FCT, here 2 FCT. Okay, 2 FCT. That means the frequency is double. Okay, so here this is one cycle. This is one cycle for this signal, 25 FCT signal. And for cos 2 FC signal, there should be two cycle because the frequency is doubled. Okay, so we have like this. Okay, so we have here like this, here like this, and here like this, and here like this. Okay, so this is a one cycle. Okay, this is a one cycle, and it is completed half of this cycle. No, so this is the half of this cos 25 FCT cycle. Okay, and we have this way, this way, this way, and this way. So this is the second half. Okay, so two cycle. This is first cycle, and this is second cycle. So two cycle is there for this cos 25 4 FCT signal. Okay. So I hope it is clear for you. Okay. I hope it is clear for you. We get like this. And here, this is one cycle. Okay. And this is another cycle. Okay. So we have two cycles. This is first cycle from here to here, first cycle is from here to here, second cycle. So here cos 25 FCT. Now we have to integrate. Okay. From 0 to T naught. Okay. So T naught we have, so you can remember that T naught we have get this value T naught. Okay. So we have to integrate this two cycle from 0 to T naught, then you can see that this part and this part cancel out, and this part and this part will cancel out also, this part and also this part cancel out, and this part and this part cancel out. Okay, so you will get 0 here. Okay, so if you integrate this 0 to t naught, you will get 0. Okay, so this part you will get 0. Okay, and what about this part? Okay, so we have PC is equal to AC square to t naught. So it is 1, no? 1 integrate with dt, that is t. Okay, so for this part you will have t, and the limit is from 0 to t naught. This is the upper limit. So you have to evaluate. So you have to substitute first this upper limit minus lower limit. That means t naught minus 0. You will get here t naught minus 0. Okay, so you will get t naught only. Okay, and t naught cancel out. You will get AC square by 2. Okay, so for sinusoidal signal, you can remember this equation. Okay, it is correct. Here, actually, you no need to evaluate. You no need to do this integration. Okay, if you can remember this. Okay, for sinusoidal signal, AC cos 25 FCT, some kind of sinusoidal signal, the power is the amplitude squared and it is divided by 2. That is the power. Okay, so PC power we can easily find 50 square by 2. Okay, so it is 100 to 50 watt. That is the carrier power. Okay. So then we asked to find. Then we asked to find the total power of the signal. So total power, we are asked to find the total power of the signal. Okay. So we are asked to find the total power of the signal. So total power means here we have two sideband. No? You can see that we have two sidebands, sideband 1 and sideband 2. Then we have to evaluate the power of this first sideband and power of this second sideband. Okay, so what happened? Okay, so if you consider first sideband, okay, if you consider first sideband, you have AC mu by 2 cos 25t FC plus FM. This you have, no? Okay. So this FC plus FM is another frequency, some kind of frequency. Let's say that it is FA or something. So you have, as a SD1, you have this kind of signal. Okay, cos 25 NEF T, like this. So you can see that this also sinusoidal signal, cos signal. So you no need to evaluate the integration. You can simply get the amplitude squared and divided by 2. So power of SB1 is equal to AC mu by 2 squared and it is divided by 2. So you will get AC square mu square, here 4 divided by 2 means 8. So you will get AC square mu square by 8. Okay, so what is this mu? Mu is AM by AC. So if you add this here, mu is equal to AM by AC and it should be also squared. Okay, and here the 8 is there. So you can see that AC cancel out. You will get AM squared by 8. Okay, so for power of sideband, first sideband is AM is 10 power by 8. So it is 100 by 8. That is 12.5 watt. No? 12.5 watt. Okay. So this is the first sideband output. Okay. So first sideband power. So if you consider the second sideband also, you can see that FC minus FM. So this is also another frequency, FB. So you have cos 25 FBT type signal. So this is also sinusoidal signal. So you can simply get the square so of this amplitude, and it is same as here. No? So for SB2 also, so for SB2 also, you will get AC mu by 2 square and divided by 2. Okay, so you will get this. Okay, so you can see that here also we get AM square by 2, that is 12.5 watt. So to find the total power, okay, so to find the total power, you have to add the carrier power and first sideband power and second sideband power. Okay, SB2 power. Then you will get the total power, that is 150 plus 50 watt. That is 100, 300 watt, no, 1300 watt. Okay, so this is the answer. Okay, then what is the next one? Okay, find the modulation index and modulation percentage. Okay, so modulation index is defined as AM by AC. So what is the AM here? 10. AC is 50. So it is 10 by 50. That means 0.2. Okay, so what is the percentage? So you have to get the percentage value. Okay, so here it is 20%. So this is the index, modulation index, and this is the modulation percentage. Okay, so we will go to the next one. So draw the full AM spectrum.